Okay, so optimization problem number 14. You have a rectangular storage container with an open top. And I haven't gone through this problem with this class, correct? Okay. Hold on, I've got to get my pen working. Okay. So I have a square top. So I'm trying to draw that in. If I have a square top, then basically I have the same dimension along the base, but a different height, maybe. And the first thing you want to focus on with optimization is what are you optimizing? This wants a cheapest container. So we're looking at minimizing the cost. So I'm going to make a formula for cost. C represents cost. And I am told, wait, you know what? I just realized something. I was assuming the square base from a recent problem that I did. We have to do volume formula. I can't. We have to do volume formula first. The volume formula will have to come into play. When I go over the problems, I try to start with what I'm optimizing and then go grabbing for other formulas, but you don't have to go in that order. You can just start throwing the formulas out in any order and eventually bringing it together. So I need to read this problem again. The length of its base is twice the width. So I'm just going to say, like, I've got x and 2x along the base. And then I don't know how that relates to height as far as with x immediately. Now, I do know that material for the base costs $10 per square meter. That means that I'm going to take $10 and multiply that by the area of the base, which is going to be x times 2x. And then I need to add to that the sides cost $6 per square meter. So I'm going to multiply $6 to how much area I have on the sides. 2 of my 4 sides are 2x times h. So 2 of them are 2x times h. Plus another 2 of them are x times h. And now I have a formula for cost. And again, it does not have a top. It said it was an open top. Now, I only have 2 variables involved for my cost, but I need 1. That's where the volume formula comes in. And you might have started that at the beginning or getting to it now, whichever, it doesn't matter. If I multiply my 3 dimensions, that gives me 2x squared times h. And then I need to decide, do I want to isolate the x or the h? And I'm going to assume that UCH is going to be a much better way to go. And then I only need to plug in to the h over here. And in fact, I might save time if I distribute the h out. So I have $6 times 2 times 2x plus 2 times x and then times the h. And the volume has to be 10, so that means that if I divide 10 by 2x squared, I will get 5 divided by x squared. And now that I have a formula for my height, I can plug that into the variable for height. And I'm going to simplify as I go along. So I have 10 times 2x squared. And in here, this is 4x plus 2x makes 6x times another $6. And then times the h, 5 over x squared. If you see me make some silly error because I just put a bunch of stuff together in my head, it frightens me that I might have messed up. So let me know if you see that. Now I have my cost in terms of one variable, but I want to simplify a little bit. It's okay. It happens. Also, John Paul, I ended up not going into the groups because people needed to see this. So if you want to go back on your phone, you can. So I have cost in terms of one variable. And then 36 times 5, you know what, I'm just going to say 36 times 5. And then times x to the negative 1. Now it's in a really nice place for taking the derivative. And I want to make sure you guys understand with the optimization, what you have at this point is something that you could graph. The x-axis is representing one of the dimensions of the box. The y-axis is representing cost. And you can imagine that the cost is probably higher. Well, you know what? I'm just going to doodle whatever the graph happens to be for my cost based on the length of this side. I'm trying to find a minimum value, and a minimum value will occur when my derivative is 0. So this is just a side note of why we are now taking the derivative and setting it equal to 0. Taking the derivative, we get 40x plus, and then negative, I'm just going to minus 36 times 5, x to the negative 2. So thank you. I appreciate that, because I'm not going to try and do arithmetic in my head while I'm trying to write this out. And now I need to find my critical numbers. To do that, I need a common denominator. So I'm going to multiply top and bottom by x on that. Yes. Thank you. That means I'm multiplying top and bottom by x squared. So this is now x cubed up here. Then my numerator is 40x cubed minus 180 divided by x squared. Now I do get undefined when x is equal to 0, but x being equal to 0 means I don't have a box. So I want to make sure that I'm looking only over a domain where my x is positive. Then I need to set the numerator equal to 0. And I'm just going to add the 180 over while setting it equal to 0. Then divide by 40. So 18 divided by 4, 9/2. And then cube root. And what is that as a decimal number? If someone can tell me the decimal number for the cube root of 9/2, I can write it down. And so I only have one critical number. I could analyze over the domain of x when x is positive. Thank you. 1.651, and cubic something. No, x is one-dimensional. What were the meters? So that is how much you want to measure x to be in order to make the cheapest container. And then from there, you'll double that number for this other dimension. And then from there, you would be able to find h based on that number. And at this point, with finding the cost of the materials, easiest thing would be to go over to where you have cost in terms of just the x variable and plug that number into those x's. And that will give you that cost. But I also want to point out that when you're in a non-multiple choice situation, when you're in free response, justification is important. So if this were a test, if this were the AP test, it would be important for you to say that the rate of change of cost is, hold on a second, let me think. We're trying to find the minimum cost, is negative when x is positive but less than that critical number, and positive when x is greater than that critical number. That would be the justification. On my test, I'm going to let that go. But I want to make sure that you're aware that the AP test will expect it if it's free response. Then let's see, where are we? Oh, so we finished that problem. We can move on to another one. Okay, dimensions of the largest area. So we have a parabola 8 minus x squared. And we have a rectangle inscribed like so. And I'm going to shade it. Now, this point right here in quadrant 1 could be anywhere along this portion of the curve. And that particular point, you can put down just some general XY ordered pair. The area of this rectangle is going to be whatever the x coordinate is, that's half of a length across. So this entire dimension across is double the x coordinate, and the height is the y coordinate. I want to optimize area. So I'm going to start off with the formula for area is 2x times y. I need a formula for area in terms of only one variable. So I'm going to take the fact that that xy point has to be on the parabola, so the relationship of them is its equation, and I can substitute whichever one I want. It's going to be friendlier if I substitute the y in. So area is 2x times 8 minus x squared. Now I have a formula for what I want to optimize. It's in terms of one variable. I'm ready to take the derivative. I would prefer to take the derivative in a nicer equation. So I'm going to distribute and get 16x minus 2x cubed. And so just to make sure you're clear, this is an area formula where you tell it the x variable on the parabola, but that x variable has to be between 0 and the intersection point. That intersection point is going to be the square root of 8. And, you know, I could put equal to, because those would be the moments when the area is 0. So they are definitely absolute minimums. And I want to find my critical numbers in this interval of x. The square root of 8 comes from the parabola is 8 minus x squared. And so setting the parabola equal to 0 will allow me to find it. Yeah, the original y equals 8 minus x squared. And so I'm looking for critical numbers only in this x interval. And those critical numbers are going to tell me if I were to draw a graph where x represented the x coordinate of this moving point, the y-axis represented the area of that rectangle, and what I should be seeing is that the area is 0 at 0 and root 8, and it will go up and then come back down. And I've got to find that sweet spot right there. And that's going to happen when the derivative is 0. So I take the derivative. And I set it equal to 0. And let's see, that's going to be 16 over 6 simplifies to, I'm trying to think right now, 8/3. Yes. And then square root, I would do plus or minus square root if I were genuinely solving that equation. But I'm looking for a number that's in this interval, so that's only going to be positive. Then on an AP exam free response, you would need to, all you would need to really do is say that the area at x equals 0 and root 8 are 0, and then say what the area is at the square root of 8/3. And then you have shown the values at endpoints and critical numbers. Now, the problem wanted us to find the dimensions of the rectangle. So then I know my x dimension. For the y dimension, I plug it back into the original parabola equation, which was, if I remember correctly, it was 8 minus x squared. And so if I plug the positive root in there, I will get 8 minus 8/3, giving me 24 minus 16/3, if I can do arithmetic right now. And double check, let me know if that was correct. Did it give units? It did not give any units. So basically just square root of 8/3 units by 16/3 units. Those, oh, no. I was almost wrong. This is the x coordinate. The dimension is 2 times that x coordinate for the length across. And then the height is then just the y. So that would be the correct answer. And I just want to repeat, you can justify this since you have particular endpoints by plugging all of these into the area formula. And whatever this one is, it's larger than 0. Now, are we at a point where I need to start the quiz? Okay, this class gets out at 10:50. Am I correct? So then 50 minus 15 is 35 after. So that's my goal. 35 after. I need to stop. If we're getting close, let me know. And I'm going to grab the next problem that was asked for, which was number 44. Yep. Okay. I might start talking louder because I had to put my earplugs in tighter because of the outside noise that I was hearing. Just letting you know. Okay. So we've got a boat leaves. It depends on if you need it for this problem. Let me see if let me read through it and then I'll tell you if I would give you a diagram. So we've got a boat leaves the dock and travels south. So no, there we go. So I'm just going to draw a dot for where it's located and traveling south. And it has a speed of 20 kilometers per hour. Another boat is heading due east, or has been heading due east. And I'm just trying to put this together. The boat leaves the dock. So this is the dock. Another boat is heading due east and reaches the dock. So heading east, reaching the dock. There we go. I suppose this would be kind to have a diagram. If I've got to read it a couple of times to figure out what it is, you need a diagram. So it is moving at 15 kilometers per hour. It wants to know at what time the two boats are going to be closest together. So I'm going to say that this point is now the dock. This is the boat heading toward it. This is the boat heading away from it. And the distance between them is right there. And do you see that Pythagorean theorem is going to be the big deal? Now, I want to focus first on what am I minimizing or maximizing. It wants to know when the boats are closest. So I'm going to put, I'll let this be letter C because, we put them as A, B, C on Pythagorean theorem. So this is going to be my focus, is an equation for C while it has these two sides changing. So I'll call this, I'll call this one A and this one B. So I have that C squared is equal to A squared plus B squared. So actually square root. And then, so I've got two time frames in here that I'm working with. I've got 2 o'clock that the boat leaves the dock. The other one is going to reach the dock at 3 p.m. So what I can do is I can figure out where is boat B at 2 p.m. or where was it at 2 p.m. So it's at 2 p.m. for 1 hour. It's 15 kilometers away from that dock. And I need to draw another picture because I have too much there. So 15 kilometers. And then that distance is shrinking at a particular rate. I am losing a distance of 15 kilometers per hour. So minus 15 times time. Yeah. Then this distance is increasing. And at 2 o'clock, the distance is 0. And then it is increasing at 20 kilometers per hour. So with all of that put together, I've got a formula for this, the two distances with respect to time based on their location at 2:00 p.m. So now I'm ready to say c is equal to the square root of 20t squared plus 15 minus 15t squared. Woo, an equation, one variable. Yeah. So I'm going to now take the derivative. And when I take the derivative with the square root part, I'm going to wind up with, in the denominator, 2 times the square root. And then I'm going to multiply into the numerator the derivative of what's under the root. So 2 times blah times the derivative of blah, or you can choose whether you want to expand and then differentiate or just differentiate with the chain rule as you go. It's up to you. Plus 2 times blah, and then multiply by the derivative of that inner function. And now I want to know what makes this equal to 0. So I'm going to then work with just the numerator now. And I have 20 times 20 times 2 would be 800 if I can do calculations. So 800t. And then I need to be careful as I distribute. So I have negative 30 times, so I've got negative 30 times 15, and then negative 30 times negative 15. And let's see, can someone give me these calculations? Because, actually, no, wait, that's 150. So 800 plus 150 gives me 950 times t minus 150 equals 0. And now I'm ready to go. 150 divided by 950. Let's see. Can someone just reduce that fraction real quick for me? Thank you. Now, remember that time is in hours. So it's this much of an hour after 2 p.m. So you just need to figure out what is 3/19 of 60 minutes. Wait, did I mess up? What did 30 times? Whoa, hold on. Where'd I mess up? 30 times 15 is 450. Oh, ha! I told you to be careful of me calculating right now. So these should have been 450. And as far as the denominator goes, yes, the denominator can't be completely ignored. The denominator is the distance between the boats times 2. If you remember that is what that square root is. And so what you can actually do is logically think about that distance is not actually going to be equal to 0. In fact, that distance is going to stay positive even when while these two are traveling. Okay, stop. I can't. Technology. So if you realize that this formula right here is actually this distance, you can see that without having to go into the algebra of it, logically, this problem will not allow that to be 0. Right. So you don't have to explain why you don't do anything with the denominator, but you should know why you can't, or why you can't ignore it. And so once those numbers get fixed up, how does that change? We get 9/25. Thank you. And then the problem wanted us to find the time. So that's where we'll go that times 60, and then add that many minutes onto 2 o'clock. And can someone tell me what they got from that? So 9/25 of 60 is 21.6. Is that it? Okay. So basically at 2:21 to somewhere between 2:21 and 2:22, they are meeting each other, or they are closest. And what did the book just round it to the nearest second? Oh, okay. Sounds good. Then we're getting close enough to time that starting another problem is not feasible. So I will make another video recording for that last problem that you wanted. And I'm going to shut this video